integrals over general regions. We've already discussed the following: how to find an integral or double integral over a rectangular region. So if we're looking down at the xy plane from above, we can think of the z-axis coming up out of the board at you, and we were interested in integrating over a region like this. Then what we could do is trace across, trace up and down here, and you can see this rectangular region on which we're integrating. And that rectangular region becomes the base of a solid. And the solid, I don't know, we'll just, in general, it might look like this. So let's redraw this picture again from a new perspective. We'll put x over here, y over here, and then z heading up. And then here's A and B, and then C and D. And we'll trace across like this. And there's that rectangular base again. Okay? And when we write something like this, double integral f of x comma y dA over the region defined by this rectangular box, we'll call it R. This is going to be the region R. What we're doing really is we're finding the volume of a solid that's created when you have the surface up here, f of x comma y equal to z, and we're sort of finding there's like a rectangular thing on the top here that would correspond to each of the corners of our rectangular region. And that shape, that 3D shape, it almost looks like a rectangular box, but it's got a wavy napkin for a top, so to speak, up here. That thing has a volume. And this double integral calculates that volume. Now, what's sort of nice about integrating over rectangular regions is that it's very easy to write down the double integral and to compute it, and there's not much to worry about. Usually we pick an order to integrate by, so we will integrate with respect to x first and then y second. So x was bounded between a and b, and then y is bounded between c and d. That's it. And then this thing will yield, well, it's an answer. I'm going to call it v for volume for now, but it's not always a volume, but that's what you have. All right. So the question today is just what happens if we don't integrate over a nice rectangular box? What if we integrate over a region maybe like this? And usually what happens is you're given some equations which bound an area for you. So for example, suppose we had the equation of y equals 2x and y equals square root of x. Now those two curves together create a region. And it will not be rectangular in shape. So again, we're going to temporarily look down at the xy plane from above and imagine the z-axis coming up at you out of the board. And here you go. So here's y equals 2x. And then y equals, I think I want to do, instead of this, let's do y equals x squared. It'll be a little easier to deal with. It's going to look like this. So you can see they cross somewhere. And then what you have is this little like crescent shape. Okay? So that crescent shape now is becoming a base. And then there'd be a solid above it coming up out of the board. And the top of that solid would be formed by the function f of x comma y. Okay? So there'd be a volume again, except you just wouldn't have a rectangular base. It would have this crescent-shaped base. And the question is, how do you set up the double integral now? Well, a couple of things. First off, we can identify some points. This is 0, 0. And then over here, at this point, if you want, you can set these things equal, or just think about it. If x is 2, y is 4, and that's true for both equations. Plug both in. Okay? So we'll decide upon a way to integrate this. So I'm going to do a double integral. I'm going to do dy first and dx second. The variation in y you get is going to vary depending on what x is. So for example, if we were to look right here at this region, y varies between that number and then that number. And then if I move over a little to the right, y would vary between this number and this number. And if I move really close to the point 0.24 maybe, between that number and that number. So this distance I'm moving in the y direction is going to vary. But luckily, I know what it's going to vary between. It's going to vary between the lower curve, which is y equals x squared, and the upper curve, which is y equals 2x. So that becomes the limits of my integration right there, from x squared to 2x. Now, just a little bit of practical advice here. When you put your limits of integration here, sometimes you have to think, okay, well, what's going to happen when I actually calculate this thing? So remember, in here somewhere is a function of x comma y. If you think about a double integral as an iterated integral, then here you go. That's the first thing we're going to compute, right? And since it's being integrated with respect to y, you're going to take the partial antiderivative of this thing with respect to y. The expression you get, you're going to sub this in for y and subtract those two values. And you're going to get an expression that will have only x in it. So if you think about that, right, if you look at this inner integral here, you're only going to get back an expression with x in it. And my claim is that's really a good thing, because the next thing you want to integrate with respect to is x. So sort of like I'm saying in practical advice, you know, choose your limits of integration here, or when you're trying to decide what they should be. If you get confused at all, think about what you're going to need once you're done with that integral. You're going to want to integrate with respect to x next. So these limits of integration better not have any y's in them, because if they did, you're going to end up with a y in your answer. So that's sort of practical advice. Now, x is going to vary between 0 and 2. Okay. Now, let me warn you. One of the things that makes integrating over general regions a little bit more tricky is when you go to change the order of integration, right? And when we think back, when we integrated over rectangular regions, there was something called Fubini's theorem, and all that said is yeah, you can switch these, make this a to b, make this c to d, just switch this to dy dx, and things are going to work out, everything's going to be the same. Okay? Well, we should be able to change the order of integration here, but you got to be careful with your limits of integration. So let's think about rewriting this another way. So double integral. Now we're saying let's do dx first and dy second. Okay. So think about what you've got to hand off to the outside integral. The outside integral's got a dy. So if the outside integral has a dy, these things here, these limits of integration, should have y's in them. Right? Okay, that's again, practical advice. What you're really doing is the following. This says dx. X is varying horizontally from here to here, or from here to here, or from here to here. Well, your rightmost function, which we know is y equals x squared, can also be written as x equals the square root of y. And your leftmost function, which was y equals 2x, can also be x equals y over 2. So now you can tell that x here is going to vary. The furthest right it ever goes is square root of y, and the least right it goes is y over 2. And that looks good to me because we know when we do the antiderivative with respect to x, plug in these expressions with y, we're going to hand off an expression that just has y in it. And then y is varying from 0 to 4. And there you go. So here we go. Let's start a new one. So suppose there's a region D. It's a good region to think about. And it's bounded between y equals 2x squared and y equals 1 plus x squared. So we have a region D that's bounded by those two things. And we say, what's the double integral over the region D of the function x plus 2y dA? So when you draw this region, this parabola is easy to look at. Here's y equals, this is an exaggerated version of y equals 2x squared. And here's another one. That's y equals x squared plus 1. So you can see that there's a region between these things. Now, you have to choose an order with which to integrate this. If we decided to integrate, let's talk about this way. Double integral, suppose you did dy dx, x plus 2y. Okay, this might not be so bad because if you do dy first, you're taking these sort of vertical slices from this volume that you would yield. And that's sort of nice because the blue parabola is always in the top and the black parabola is always in the bottom. Not bottom, but bottom. And that looks pretty good. This would be a nice way to set things up. Let's just consider the other order for a moment. Suppose you want to do dx dy. Okay? You're going to run into a little bit of trouble here. Here's why. If you switch the order here, then the issue you're going to have is, here we go. I'm going to do right minus left. That looks pretty good. But then up here, things get a little bit tricky. Because if you look at this horizontal line I've drawn, it goes outside the region of integration. So you could eventually get this to work, but you're going to have to be very clever about it and break this thing up into different pieces. I think here it's clear that this is the better way to go, to use the green slices instead. Okay, so if we commit to that, then y is varying between 2x squared and x squared plus 1, as x varies between something and something. So we need to know what that point of intersection is and what that point of intersection is. You get that quickly by looking at this. You get 2x squared. We want that to equal x squared plus 1. X squared equals 1. So x is plus or minus 1. Here's negative 1. Here's 1. So there you go. So here we go. This thing, with respect to y, so if y is the variable, the antiderivative becomes x times y plus 2y must have been the derivative of y squared. Okay, that's pretty nice. And we're going to evaluate that from 2x squared up to x squared plus 1. So we're going to sub some things in here and do some simplifying. So when we plug in the top expression, we get x times x squared plus 1 plus x squared plus 1 squared minus, now I plug in the bottom expression. So we get x times 2x squared plus 2x squared squared. Okay, so sparing you all the stress, here's what you end up with. So that thing is what happens when you collect all the terms in this expression. We're going to take the antiderivative from negative 1 to 1 of this expression. Okay. All right. So that is just, some basic, that's a basic antiderivative from back in single variable calculus. You go through term by term, take the antiderivative, plug in 1, get an answer, plug in negative 1, get an answer, subtract them. When everything's said and done, you'll get 32 over 15.